All right, our next speaker is Toby Harris. He is the Global Head of Space Situational Awareness at Astroscale UK and Europe. He's responsible for ensuring SSA needs for current and future missions and for developing and implementing Astroscale's SSA strategy. Toby was previously head of orbital systems with the Chief Engineer's Office at the UK Space Agency, where he oversaw technical aspects of licensing UK spacecraft, helped develop the UK licensing process and UK spaceflight policies, and supported the creation of the 2018 Space Industry Bill. Toby has headed the UK delegation to UN COPUOS Scientific and Technical Subcommittee, and represented the UK as policy lead for the Interagency Debris Coordination Committee. Thank you for being here, Toby, and sharing your presentation across multiple space debris conferences even this week.
Thank you. Yeah, I think I've got 6 of them or something like that, but they're all slightly different. They're all tailored to who I'm speaking to. So hopefully there'll be something different in each one. Brilliant. So shall I share my screen in that case?
I'll let you know when we can see it. It's up and not yet in presentation mode. There it is. Looks great.
Brilliant. Okay, so as Lee said, I'm head of SSA at Astroscale. Been there since November. I'm going to speak a little bit about ELSA-D, our recent spacecraft launched to test and demonstration technologies, and also how that particular mission is going to help develop some of our SSA capabilities in the future. So just a brief introduction to Astroscale for those of you who haven't heard of us before. We're a commercial venture with a focus on space sustainability. Our mission is to develop new technologies and advanced business cases, look at international policies with the goal of trying to reduce orbital debris and trying to support the long-term use of space. And obviously our vision is in line with that, securing safe, sustainable development of space for the future. And space situational awareness plays an important role in Astroscale's, in our missions and what we intend to do in the future for 2 main reasons. First of all, we need space situational awareness to meet our mission goals. We can't perform our missions without having that capability, and I'll explain to you why shortly. And then secondly, we want to be able to use the missions that we're developing, not just for active debris removal or end-of-life services, but also to look at how they can contribute to space situational awareness and missions. So I'll give you a quick overview of the type of missions that Astroscale are currently involved in. It's quite a busy slide, so I'll work through it kind of slowly. So we're an international company at Astroscale. We're based in the UK, in the US, Israel, Japan, and Singapore. We have subsidiaries all over the place. And each area is kind of developing missions in parallel with one another, focusing on slightly different areas. So in the UK, for example, and Japan, we've been working on ELSA-D, or rather have been working on ELSA-D, which was recently launched in March. Again, I'll speak about in a bit more detail in a second. Also in the UK, we're currently working on a UK Space Agency funded active debris removal mission. So it's early phase 0, phase A study at the moment, with the goal of developing a further mission in 2025. Also in the UK, we're looking at what's called ELSA-M. So ELSA-D is the demonstration mission. Following on for that is the ELSA-M, which is a multi-client mission. This will be subsequent to the success of the ELSA-D mission, and will basically involve us working alongside OneWeb and ESA to look at actually deorbiting or performing an in-orbit demonstration mission of deorbiting a spacecraft. In Japan, we're currently looking at the ADRAS-J mission, which is an inspection mission. So the goal here is to actually go up to a defunct Japanese H-2A upper stage and then inspect the rocket, the body itself as part of this CRD2 JAXA-funded project, and that will be launching in 2023. And then following on from that will be ADRAS-J2, we hope, which would be the actual deorbit of this rocket body. So rather than just going up and inspecting it, the service will go up there, capture it using some sort of mechanism, and then deorbit the whole rocket body into the atmosphere. But in the US, the focus is mainly on life extension in GEO. So in Japan and the UK, the focus is on LEO, whilst in the US, we're looking more at GEO. And this is the development of our Lexi spacecraft. And this is supported by Astroscale Israel, who were actually originally Effective Space and bought out by Astroscale a couple of years ago. And the goal is to launch our first life extension mission in 2023 to go to geosynchronous orbit and stay there for about 5 years, extending the life of a client up there. As well as the missions themselves, we're also developing our National In-Orbit Servicing Operations Facility in Harwell, just a few miles from me in the UK. And then in the in Japan, we're also developing our ground segment with the Totsuka ground station in Yokohama. So ELSA-D, I mentioned it a few times. We like to think of it as the world's first end-of-life demonstration mission. Now, there's a subtle difference between end-of-life and active debris removal. Active debris removal is generally the idea of going up to a random piece of junk that's up there, grabbing onto it somehow, and then removing it from orbit. End of life is where a spacecraft has been pre-prepared in advance to be deorbited. So it might have some sort of docking plate attached to it or some sort of mechanism that enables it to be captured. So it doesn't require a robotic arm or a net or some other abstract system. It would be designed to be removed, and so it would have to be done in advance of the launch. So ELSA-D is actually demonstrating technologies for both active debris removal and end-of-life demonstration, but the goal is to follow on to this ELSA-M, which would be an end-of-life mission. So the mission itself consists of 2 spacecraft, a servicer and a client. There's a ferromagnetic docking plate, which is on the servicer and connected to the client. So the 2 spacecraft are currently launched together. It was successfully launched on March 22nd, designed to explore a number of different key operations for an end-of-life service. So including client search, inspection, capture, reorbit, and then end-of-life deorbit. It's licensed to the UK Space Agency, includes a number of partners, including UK-based companies such as SSTL, as well as GMB, CGI, REA, and various others. And it's currently being operated at the National Orbit Servicing Control Centre at the Catapult. So just to give a quick run through of the ELSA-D mission itself, there's quite a number of phases to it, 7 phases, and there's sort of 3, well, there's now 4 because phase 3 has been split. There are these 4 demonstration phases, which are kind of sort of the meat of the mission, as it were. And so I'll talk a little bit about where we are at the moment in just a second, but for the time being, we have the LEOPS phase, we have the commissioning phase, and we have phase 3A, which is a simple manual capture of the target. So initially the 2 spacecraft are docked together at the moment, and what would happen in phase 3A is that the target would simply be detached and then recaptured again. I'll talk about that in a second. Phase 3B, which will be subsequent to that, involves the disconnection of the target and then reconnection again, but with a certain distance between the 2, and it would involve onboard autonomy of the spacecraft as well. Again, I'll talk about it in a little bit more detail in a second. Phase 4 is kind of the next step, the slightly more advanced mission. So in this case, the spacecraft would be separated, and then the target spacecraft would actually be put into a tumble motion. So it'd be rotating about a spin axis. And then the goal then is to actually maneuver the spacecraft, the servicer, to the client and actually move it into a local orbit about that tumbling object. So it's quite a complicated bit of guidance and navigation to ensure that it does this. We call it the dance maneuver, where it's actually moving around in a local orbit about that object, at which point it will then connect and dock with the spacecraft together. And then the final demonstration, phase 5, is kind of like everything put together, where we would disconnect, we'd put it into a tumble, and actually we would try and lose the target. So the servicer would move into a different orbit, only a slightly different orbit, move a certain distance away, and then it would rely on its relative navigation equipment and onboard sensors to find the target, maneuver into the range of it, perform the dance maneuver to try and synchronize itself with the target, and then dock with it to complete the mission. And so at the end of that, once all those mission phases are completed, it will perform a descent burn and then naturally decay into the Earth's atmosphere over a number of years and then passivate. So where are we at the moment? So obviously we've launched. So pre-launch is all done and dusted. Phase one with the launch and early operation phase. So there was no problems there either. We had good signal acquisition, solar array deployment, and the orbit was successfully injected into the correct area. Just for those in the know, 550 kilometers sun synchronous is very, very close to the Starlink constellation. I think it's just a few kilometers away. And so we've made sure we've coordinated with those spacecraft and others in those kind of orbits. And then for the most part of the last 4 months, we've been doing the commissioning phases. So testing interface with the ground segment, ensuring the subsystems are calibrated, and ensuring the client's activated okay. We've just recently completed the phase 3A demonstration on August 26th, and we are now currently looking at when to do the phase 3B demo. And so I've kind of talked about this in a little bit of detail already, just a bit more information there. So on August 26th, the client was separated from the service of the first time, and it was manually captured. So this means that it wasn't using the onboard software to do it. It was doing it purely through the telemetry, telecommands from the ground segment. And so during this mission, during this particular demonstration, we checked out and calibrated the rendezvous sensors, and then we verified the relevant ground systems infrastructure and the operating procedures. Phase 3B, which will be hopefully in the next month or so, will be something very similar, but the distance will be greater. So this one, it only lasted literally 15 seconds or so, this particular demonstration. The next one will be quite a bit longer than that. There'll be a larger distance between the two. And we're actually hoping that from a ground-based observation perspective, we'll be able to see separation between the two objects as well. And this time it will be using the onboard autonomous software to actually dock with the target. So it won't rely just on ground telemetry. And the reason is, when you're relying on ground telemetry and telecommands, you have to wait for a pass, and you only have a few passes per orbit. We actually have a total of 12 or 16 ground stations for these missions. So we've got as much coverage as we feasibly can get for this type of mission. Normal missions don't have nearly as many ground stations. So we have got quite a lot of pass coverage, but what we'd like to do is try and to use that as a redundant capability and try and do as much of this work on board using autonomous software as possible. Okay, so how does this relate to space situational awareness? So any mission, SSA is fundamentally important. The rendezvous and proximity operation missions such as LCD also have significant additional needs. And actually any mission involving a second spacecraft in close proximity will sort of need these additional SSA capabilities. And we want to try and use LCD to try and explore what those capabilities need to be and how we can access those needs, as it were. So I won't go through this table in too much detail. This is kind of a work in progress to try and understand what kind of accuracy and precision and frequency of data we need for space situational awareness. And I've kind of sort of labeled different color coding there. So blue is basically indicating this is a kind of a standard SSA product, as it were, that most missions require. So understanding where your spacecraft is, so in this case, the service to state, and also providing collision avoidance capabilities. So using an SSA provider to screen against other objects in the orbital environment. And then we also have launch collision avoidance for the initial launch phase and space weather analysis if, for example, that was something that might be an issue for the mission or something that's important in terms of scientific study. The orange ones there are ones that are more focused on the rendezvous and proximity mission itself. So the client state, where that client is in relation to the servicer itself. It becomes less important when they're in close proximity because you're using relative navigation on board the spacecraft. But when they're further away, you need SSA to try and know where you're heading to if you're moving between orbits, for example. Also, another important one, less important for LCD, but for other space missions in the future, particularly active debris removal, is looking at the attitude rate of the climb. If it's spinning in an unstable or quick rotation, then it might be a very difficult object to capture. And so that's one of the things we need to understand about it. And so that's where SSA can play a part. And then also the collision avoidance when you're in close proximity to another object also needs some subtle understanding of how that should work. When you're moving around, perhaps performing a collision avoidance, or you have a conjunction warning just before you're about to do a demonstration or during the demonstration, you need to be clear on how the processes are set out for that kind of event. So these are all the kind of things that we're sort of looking at the moment. And so we want to be able to try and meet some of these RPO SSA needs, and we want to use ELSA-D to try and do some of that. So at the moment, ELSA-D is providing us with lots of interesting ground truth measurements. We have the GPS position, and we have the attitude and tumble rate, so that's telemetry from the spacecraft. And we also have access to other data that's either derived from that or might be considered specific state data from, for example, laser ranging stations. So we have also, as well as that, the burn and maneuver schedule of the spacecraft. So we have quite a lot of what I consider ground truth measurements of the spacecraft. What we want to be able to try and do is combine that with SSA observations from existing systems or novel ground-based sensors and even space-based sensors, and basically try and validate novel systems, trying to work out whether we can calibrate sensors for these kind of missions and develop new capabilities for RPO missions. Now, at the moment, it's pretty much business as usual, but in the future, when we're doing these sort of phase 4 and 5 demonstrations, where spacecraft are moving apart and moving together and doing these dance maneuvers, it's going to be quite interesting to see how the ground-based systems reflect what's actually happening for ground truth. And so just a quick aside here, in terms of our ground-based SST COLA support. So obviously space safety is top priority in developing the ELSA-D mission. So we perform conjunction analysis and coordinate and share data with various other spacecraft operators and SSA service providers. We currently work with ESA and the 18th Space Control Squadron, as well as liaise with NASA, and also have a contract with SpaceNav providing us advanced SSA information. That's particularly important given the orbit where we're in, the rather large amount of traffic of other spacecraft in that area. We need to be clear that when we're doing these demonstrations, that it's safe to do so. So at the moment, we are in almost like a stage of trying to gather SSA data, help calibrate those SSA service providers, so we can begin to use this information when we actually perform the demonstration phases. So we've been using space track data through the 18th Space Control Squadron. We've been working with Leo Labs, EUSST and AGI Comspot to use their observations and to use our telemetry to understand more about how this mission is going to look like in the future, and how we can use their services or develop their services to support these kind of missions. And this is going to be particularly important for us as we look to the future with the ADRAS-J mission, actually removing rocket body, and then the UKSA ADR mission, again, which will be looking to remove a defunct UK spacecraft. As well as radar observations, we've been liaising with the International Laser Ranging Service and the Austrian Academy of Sciences, GRAS, and they've been providing us both satellite laser ranging observations as well as light curve data. And the light curve and photometry data is quite interesting. It's one of the things that we are keen to explore more in the future. As I said, one of our key sort of client SSA requirements is understanding the tumble rate of the target. So understanding how these defunct objects are moving in advance of launch, and also taking observations before launch and then predicting what that tumble rate might look like when the spacecraft's actually there, because it might be 6 months, it might be a year between when the observations are made and when the spacecraft actually gets to its target, will be quite important. So this is another area that we're really keen to explore. We've also been working with a company called Share My Space based in France, who've been doing some similar LEO optical observations. They're currently calibrating for photometry, and you've kind of got an image there on the left of a short streak of ELSA-D crossing the night sky from the 18th of July. And again, this is trying to understand how we can use their capabilities in the future, perhaps calibrating against ELSA-D, and to understand how it can be used for future missions as well. As well as doing ground-based work, we've also been working with a company called HO Robotics in Australia to look at space-based imagery. And they're actually using a novel approach to imaging objects in orbit using Earth observation cameras, observing spacecraft as it flies past. And so this takes quite a bit of ingenuity and timing and image processing. And they recently captured an image of ELSA-D. So here in the sort of 60-frame video, as it sort of scooted past at a relatively slow 45 meters per second, which is phenomenally slow given how fast most of these objects move past one another. We're kind of interested in this for two reasons, mainly because we want to look at whether we can use space-based resolved imagery to observe potential future active debris removal targets. So identifying the craft condition, any structures that might be used for load bearing, any anomalies that might make the target difficult to capture or attach onto. And we also want to use this for transparency and confidence building. RPO missions, obviously there's a very gray area between civil activities involving rendezvous and proximity, and also the sort of counter space type area as well. And so being able to observe the missions as they happen in using resolved imagery or using space-based capabilities is something that we'd be keen to investigate further as a way of trying to provide that third-party reassurance of what our missions are all about. And finally, we're also looking at whether we can use the cameras on board LCD. These are basically visual cameras used for, like I said, relative navigation and pose estimation of the target, whether we can use them for broader SSA purposes. Can they capture objects in geo? Can they capture objects moving around? And can we use that to augment ground-based sensors? So this is something where we're kind of trying to repurpose the existing sensors and perhaps understand how they could be modified or augmented in the future to provide almost like an SSA platform as a secondary purpose for the mission. And this kind of also extends to the idea of almost like a distributed architecture of in-orbit SSA satellites. If everyone has a camera on them, can we use that to augment ground-based networks and provide a much better view of what's happening in space? And we're working closely with ESA on this to see how we can develop this capability. And so that's my summary. I think that's about all from me. So basically, just in summary, obviously we recognize the importance of SSA to RPO missions, particularly ADR and end of life. We're still developing SSA requirements for future missions, and we're trying to use LCD as much as possible to support this. And we're also very keen to collaborate with both SSA service providers and other spacecraft operators to help better understand this. And finally, we're trying to use the capabilities on board the spacecraft on LCD and in future ELSA-M and ADRAS-J to see whether we can repurpose those instruments to support in situ SSA. And I think that's about it. Thank you very much.
Thank you very much. We've heard throughout the day a little bit about where things are, solutions for specific capture and recycling mechanisms, but to have it placed in this overarching presentation about what space situational awareness is and encompasses, as well as to know the broader scope of Astroscale's mission is really helpful in understanding the big picture about the space debris problem. So thank you very much.
No problem.
We talked earlier today also about the legalities, the difficult situation when you're pulling down something, deorbiting something that may have questionable ownership or isn't directly owned by the entity working on it. Talk about what you needed to do from a legal standpoint to prepare for the ELSA-M mission. Whose rocket body is that? And what permissions did you need to get, or are you working on getting for that mission?
Yeah, sure. The legal issues are always very tricky. I remember working on some of these legal issues when I was at the space agency, and I'm quite glad I'm on the other side of the table now, actually, because it's not trivial by any means. So ELSA-D is obviously very trivial because they're both our spacecraft, so there's no problems there. Any liability and what have you is purely on Astroscale. ELSA-M is it's a partnership with OneWeb and through ESA and funded by UK Space Agency. So that's going to involve a contractual agreement with OneWeb, who are technically licensed by the UK Space Agency. And so from a liability point of view, it's basically a single nation, so it shouldn't be too much of an issue. I think that's, again, where things can become quite complicated when you're involving international liability issues and international problems potentially. And with ADRAS-J, which is going to be Astroscale's deorbit of a Japanese rocket body, again, the mission's likely to be licensed through JAXA. It's a Japanese rocket body, and so hopefully there shouldn't be too many issues with that either. Again, if something goes wrong, it's going to be on Japan ultimately to be accountable for that, and also Astroscale Japan as well.
Mhm.
I think the real problem comes when you'll start talking about service that involves, another company from another nation. There will be contractual agreements you'll have to have between the commercial entities, and then there'll potentially have to be MOUs between the licensing nations as well, or some sort of agreement there as well. Certainly, it can become very, very complicated when you're involving a third party, or in fact, even a fourth party into to mix as well. And so I think in the future, when we're looking at ADR missions of third party objects, perhaps ones with ambiguous ownership, is going to be very, very difficult. Obviously, in space, everything is technically owned, although it's not necessarily clear who owns what sometimes, particularly after fragmentation. And so these are the kind of things that have to be worked through at, I guess, not just the national level. I know that UK Space Agency is doing some work on this, but I think international agreements can be key on this.
Great. And Michael Lane had a great question about some of the acquisitions that you've made. You talked a lot about partnerships in executing the work, and sounds like you're drawing a little bit of those into a vertical integration system. So, talk a little bit about your investment criteria for acquisitions and where you see that going forward.
Okay, I will do my best. That's a little bit out of my
A
remit of
a
knowledge
little
there.
out of your window.
So I certainly know that Effective Space, who are based in Israel, were developing a life extension spacecraft. I can't remember the name at the time. And this was in an area that we felt would complement the active debris removal and end of life capabilities that we're developing already. And that's where I think that the idea that we would then almost partner with, buy out, I guess, eventually, Effective Space and make that part of Astroscale US. And I think that was also part in light of the MEV mission by Northrop Grumman in the US. And so I think the idea was to almost work alongside that mission and develop capabilities in the US there. I think from UK and Japan side, I don't think we've made any recent acquisitions as of yet. And whether or when we're going to make any acquisitions, I'm not sure. Again, that's a little bit outside of my remit of knowledge, but we'll just have to wait and see, I guess.
Yeah. Well, thank you for the attempt at it. Appreciate it. You talked a little bit about in the mission about driving policy, and this ties back to talking to the public, Astroscale. You said you're giving 6 presentations. You have a podcast, not you, but Astroscale has a podcast to talk about these issues. Why is public engagement important to the space debris problem?
I mean, I think in some ways it has a parallel to climate change, I guess. You've probably heard that before, and I think it's quite true in some ways. In one way, they're very different problems, but in some ways there is a common, certainly from a policy point of view and a public engagement point of view. Once you get a critical mass of people saying this is a problem, something needs to be done about it, that's when governments tend to step up and do something about it. And I think there are conscious efforts at the moment in the international community to do something about the space debris problem. And again, it does parallel climate change in that way. Everyone needs to do their part. It is a global problem. I think the difference with space debris is that it's less impactful on people in their general lives. Space debris, you hear about it on the news every now and then, but it's not something that's going to affect your day-to-day life. Whilst potentially climate change, as we've seen recently with floods and various other bits and pieces, really does. So I think it's really important to make sure that people are aware that it is a problem, even though if it's not right in their face every day. It is something, again, a bit like climate change. It's something that we can fix really, well, much easier now than sort of 10 or 20 years down the line when we had one or two more significant collisions, which are causing havoc up there. So I think it's really important to keep that public engagement going and make people as aware as possible of the potential future issues.
Great points. Thank you. And it sounds like with the Address J and Elsa M, there will be some spectacular shows in the sky coming up. Can we get alerts on our phone for when to look into the sky at night?
We do have a map on our website actually that shows where Elsa D is at the time. And I think there will be some communications about when we're doing these demos. So hopefully if you've got a telescope that can track a LEO spacecraft, then look out for those announcements, and perhaps you'll be able to see a couple of dots move apart from another and then join again.
Thank you so much for being here today, Toby. Really
No
appreciate your
problem.
time.
Thanks for inviting me.